that's one thing I'll hear about. But if you want to bring coffee or something to drink, and if you're going to bring a breakfast snack or something like that, please make sure you collect all the crumbs and don't leave a mess. Besides that, I'll tell you where we're supposed to start. When we in this course, we're supposed to start in chapter 6, plane waves. Now, those that have me, I've already started doing the plane waves propagation. But this is important. And are there any questions before I get going? I feel like I'm forgetting something. Oh yeah, I use OneNote exclusively. I mentioned that. You have the link. I put the homework up. You'll see homework 1, 2, 3, 4, and so forth, and all the information there. I will. I'll post additional pieces of information on there that you may need, but it shouldn't be a problem for anybody. Any questions before I get going on the subject? It's a tired, quiet class. 8 a.m. comes too early. I don't like it either. I couldn't believe I got in there. This is usually reserved for the assistant professors of the lectures. Anyway, so now what we're going to do, we're going to start in chapter 6. We're going to develop a propagating wave equation. I'm going to just tell you where we're going with this. The way I do it a little differently than Dr. Wentworth. I come out and I'm going to just say that all the things that we do in EMAG 2 and EMAG 1 are based really on Maxwell's equations, all right? And they're based on 2 equations. The first is curl of H is equal to J plus partial of E with respect to T. That's one equation. And the second is curl of E is equal to minus dB dt. Now, those 2 equations basically govern all electromagnetic field behavior, really in the macroscopic world, but even in the microscopic world. There's links between these things, the different parameters. For instance, J is called the current density and is equal to sigma E. And E is the electric field intensity. There's also the linkage between D is equal to epsilon E, where D is a magnetic flux, or I'm sorry, electric flux vector, and E is the electric field volts per meter. And then there is B is equal to mu H. Now you've seen those before, right? Everybody? These are the things that link really one quantity to another in terms of the material parameters. Sigma is the conductivity, and it really tells you how conductive a region is. The larger that value, the better current flows in that region. Think of it that way. Epsilon is the permittivity. Now, epsilon and mu, epsilon is really epsilon relative times epsilon naught, and mu is mu relative times mu naught. Here, mu naught and epsilon naught are based on the values in a vacuum. And I think most of you know this, that epsilon naught is equal to really 1 over 36 pi times 10 to the minus 9 farads per meter, or epsilon naught is equal to about 8.854 times 10 to the minus 12 farads per meter. And mu naught is really 4 pi times 10 to the minus 7, and that's henries per meter. Those are the values of free space for epsilon and mu. And sigma is really a materials parameter. If it's in a vacuum, sigma is 0. There can be no real current flow in a vacuum. Y'all follow me on this so far? This is just, I'm restating things you've heard already. Now, with these equations, does anybody remember what this equation is called? There's a term for it. It's a very famous man. There's 2 very famous men involved in these things. This is Ampere's circuital current law. You know the name Ampere, right? That's where we get Ampere. This is Michael Faraday's law of induction. Right? Both of them are based on measurements. Remember that. Everything we do here is based on measurements. Nothing's based on, like, it just, came down Mount Sinai, here's the 10 Commandments plus a few others. These things are strictly based on measurements, but they're exact, mathematically exact. So what we're going to do now is take those equations, and I want to make one really important comment here. When you have magnetostatics or electrostatics, there's no time variation. That term's not there. Then you get curl H equals J. Y'all remember that? That's where you use Ampere's law. You would find all the current that would penetrate through a symmetrical loop was equal to what? The integral H dot dl around that loop. Do y'all remember that? Right. But this term is necessary to make this equation work when there's time variation in the electric field and magnetic field. So now what I'm going to do is take those equations and turn them into one single equation, but I'm also going to do something. I'm going to do this in the phasor domain. Now, what I like doing, and some people wouldn't do this, but I think it's important. When I talk about phasor domain, the first time you were exposed to it really was in circuits. How many had Irwin for circuits? Almost all of you. All right, well, the phasor domain is something where we assume that we're exciting a circuit using a steady sinusoidal or cosinusoidal varying waveform. Do you all follow me on that? It's a specific frequency and one frequency only. So when we solve a circuit in the phasor domain, and suppose I have like V naught cosine of omega t plus some phase angle here is the voltage, and I have a resistance here, R, and I have an inductor here, L. Okay. So, by the way, I say this, and I'm serious about this. Oftentimes, if you go for a job interview, what they'll do is give you a set of problems, and they're going to ask you to work them, and they'll watch how you work them, and they can tell right away what your level of understanding is. So what they'll ask for typically, not always, they might ask for the current I as a function of time. So this is what they want you to find, just to make sure you're what you say you are. Now, if you're a physicist, you're probably going to write a differential equation. And you're probably going to solve the differential equation either with an integration factor or using Laplace transforms, if you're a physicist. Now, electrical engineers can do that also. But the one thing you're taught from the get-go in circuits is that's at a constant frequency. Do you all agree with that? I'm just using omega. Typically, it's really 120 pi for 60 hertz, isn't it, class? What is typically done is you don't solve this in the time domain, do you? You put it to the phasor domain. Do you all remember that? And in the phasor domain, that voltage source becomes what? It becomes plus or minus the value magnitude V naught, and then it's at an angle of whatever that phase angle is. Do you all remember that? Now we've eliminated frequency. Do you all remember? I'm not going to go through how you do it. I mean, we can if you need to. See me in my office after class. Then the resistor is going to just look like a resistor. And what happens to the inductor? What do we replace it with?
Impedance.
Yeah, and what is the impedance? You're absolutely right.
J omega L.
Do you all remember this? J omega L. So now I put down the impedance here is J omega L. And now I solve for the phasor current, don't I? I solve for the phasor current. And when I do that, what do I get? I get I phasor is equal to the voltage, V naught at that angle, whatever the angle is, and it's divided by R, right? Plus J omega L. Now, that's a complex number. It has a magnitude and an angle, or it has a real and imaginary part. You all remember this? We've still not back in the time domain. What I'm going to do is say, at the end of the day, when we have this, we're going to get one quantity, some I naught, and it's going to be at an angle, some, and I'll call it theta I. I made sure I left this general. We could put down specific values, but you all remember doing this, right? I'm going to remember doing this particular problem, this type of problem. Everybody? Okay? Now, at that point, how do you get it back to the time domain? That's not time domain, that's phasor. Well, technically, what do? I'll put it here. You say that I of t is equal to the real part of, this is the technical way to do it, of e to the j omega t times I phasor. This is the technical way to do it, right? Now, I of t is equal to the real part of, and I'm going to put down e to the j omega t, and then I have I naught, and you all know that angle can be rendered as e to the j theta, right? You all remember this? that would be exponential notation. What I've shown you there's polar would be times e to the j theta I. Then I'm going to go down, I'm going to combine them. I'm going to say I of t is the real part of, and now it's going to be some magnitude I naught e to the j of omega t plus theta I. Right? Not quite done yet. What is my next step? Some of you know. Remember that e to the j theta is equal to cosine of theta plus j sine theta. Do y'all remember that? What's the name of that identity? Anyone? Famous guy. Euler's identity, right? You remember Euler's identity? All right, now the real part of this expansion is just cosine. The imaginary part is sine because there's a j in front of it. Y'all follow me in this class? Okay. So when we take a look at this right here, we see that I of t, once I expand this in terms of a cosine plus j sine, the real part of it is just the cosine. Do y'all follow me in this class? So this means, when I'm all done, I simply get I naught cosine of omega t plus the phase angle of I. And now we're in the actual time domain, and that would be the time domain solution for the current there. That's the way you would solve it if you were given that problem. But this type of thing, believe it or not, if people, oftentimes with Dave Irwin's book at least, he never asks for the time domain form. What he'll do is just ask for the phase domain all the time. Do y'all remember doing that? It was, the time domain was something at the beginning he showed the interrelationship, and he never went back to the time domain requirement. Do y'all remember doing this kind of stuff? But it's important that you see that. Well, this is doing a problem in the phasor domain. Now what we've done is, I mean, really, if we take a look at the relationship between current and voltage in that inductor, we know that what? V of t is equal to L times di dt, right? Isn't that the general relationship for current voltage in an inductor? V is equal to L di dt, but where we had di dt, replace that with what? J omega, right? Because everything is now assumed to oscillate as an e to the j omega, and that means the time domain derivative there, this would turn into simply V phasor is equal to j omega L times I phasor. So anytime you have a time domain derivative, you replace it with just j omega. Y'all follow me on this? How many remember this? No? You're looking like, I don't think I'm there. Well, I mean, do you remember doing this stuff where you would write the equation, the differential equation in time, and then you would substitute in the phasor assumed solution for I. It's going to be I e to the j omega t, right? And every time there's a time derivative, you pull out a j omega. Do y'all remember something like that? That's the way it works, and that's how you get it. So now I'm going to go back to these things and create one equation with one unknown. But it's going to be in the phasor. So I come over here, I've got two equations, two unknowns. Now, well, I guess I'm going to do this in stages. The first thing I'm going to do is replace J with sigma E and D with epsilon E. And then here, I'm going to replace B with mu H. Y'all follow me? So this first equation, curl of H, will be equal to sigma E plus epsilon times dE dt. Here I'm replacing D with epsilon E. And I get curl of E is equal to minus mu, and it's going to be times dH dt. So now I've reduced the number of unknowns. I've got really, I'm assuming that sigma, epsilon, and mu are known. They have to be, or else you can't solve these things. And now I've got two equations with two unknowns, correct, class? Now I'm going to take them and put them into the phasor domain. That's my next step. So, and I'll do it over here. Now the curl of H equation becomes sigma E plus j omega epsilon E And furthermore, I can break that, I can combine terms and get sigma plus j omega epsilon times E. And then I get curl of H, I'm sorry, curl of E, pardon me, curl of E is equal to minus j omega mu times H. Go ahead and take a look at that. Those, both in the phasor domain, I've replaced the time derivative with a j omega. Y'all follow me? Everybody follow me on this? My goal is to create one equation with one unknown and then get the solution to it. I'm gonna have to do a few other things too in the meantime, but y'all with me? Y'all follow what I've done, okay? Any questions? All right, now to get one equation with one unknown, what I'm gonna do, this is E here. Does anybody have, some of you know this because I've done this before. How would you do that? I want one equation with one unknown. I want you to take a look at something. Anytime you're ever confronted with this in mathematical stuff, because some of you you're gonna be doing higher level math a lot in your engineering work. Always take a look at what you can do to an equation to have a term that resembles something in another equation that's there that also governs behavior. Well, if I take another curl of this equation, if I get curl of E, that's minus j omega mu times curl of H, isn't it? I've taken two curls. Now I'm assuming that mu does not vary spatially. If it did, I couldn't do this. If mu was a spatial function, then I could do the curl of that, it would be more terms, all right? But I'm assuming it's constant. Do y'all follow me what I've done there? Now what's my next step? This I'm pretty sure you see. Go back to the equation that is untouched. You'll notice there's curl H, right? Take that and stick it here, and now I have one equation with one unknown. So I simply say that curl of E is equal to minus j omega mu, and then curl H becomes this times sigma plus j omega epsilon times E. And now I have one equation with only one unknown in terms of the field quantities. I have one equation in E. Everything else is material parameters. Do y'all follow me, class? That's based on Maxwell's law. By the way, James Clerk Maxwell, long before a lot of the really precise measuring devices we had became available, and that we had this around 1920, 30, and 40, he already could derive the speed of light just from those two equations, and won't do that. Those two equations give you all the information you need. As a matter of fact, even with general relativity and special relativity, these equations hold true. Okay, so now I'm going to take this equation and I'm going to break it up a little. Now I have curl of E right here becomes the gradient of divergence of E minus del squared of E. This is a simple vector. It's a vector identity. You don't have to take vector calculus for this class. I mean, you don't have to take it in your engineering curriculum. Long ago you did. But in vector calculus, you learn all sorts of vector identities for the del squared operator, which is called the Laplacian.
We kind of did it in Calculus 3, like not, maybe not as in depth.
Did you guys do this kind of stuff? You did Stokes there then? Or not?
I think we did.
It's a little bit in the linear algebra as well.
Oh, yeah.
Is that right? Good, I'm glad to hear that. Well, anyway, I'm taking this and I'm breaking this down to the gradient of divergence of E minus del squared of E, and that's equal to minus j omega mu times sigma plus j omega epsilon times E. Now we're going to start introducing assumptions and new constants so we don't have to keep writing that mess over and over again. So the first thing we do is I want to get one constant that really could lump all those material parameters and frequency parameters there. And it's called gamma. Gamma is the propagation constant. It's equal to alpha plus j beta, and it's actually equal to the square root of j omega mu times sigma plus j omega epsilon. So remember, this is called gamma. It's the propagation constant. And it's equal to alpha plus j omega. You'll see why it's important to break it out like that. But we're giving it as j omega mu times sigma plus j omega epsilon. Now that's what's in front here. So now I can rewrite that side of the equation simply minus gamma squared E over here. Y'all follow me what I've done? Right, the only thing I'm doing is I'm creating something that makes my life easier, constant that takes care of all those terms, so I can just work with that constant. Now, after that, on this side, the next thing I do is assume the region is charge-free. So we're assuming when we solve this, we have a charge-free region. By that, I mean rho v is equal to 0. Now that's pretty much true in the atmosphere. It's true in almost all standard materials that don't have some inherent current source in them. And I'll spend a little more time on that later. So when we have a charge-free region, we know that there's something that's important. Do you remember what is divergence of D equal to? Do you remember what that is? Very important law. These are things you'll have to know very well, by the way, before you get out of here. Divergence.
Isn't like the partial of
Divergence of D is rho v, right? This is Gauss. I mean, do you remember this? This is when we talk about Gauss's law. You're used to seeing the integral of d dot ds over any closed surface as the charge enclosed, right? Do you remember that? That's the integral form of it. That's the differential form of Gauss's law, the point form. Divergence of D is the charge density. Now, if the charge density is 0, it means divergence of D is 0. It also means divergence of what? E would be rho v over epsilon, and that's also assumed 0, okay? Remember, this is Gauss's law. It's so important. And these are things you're going to have to put on well, especially as we get towards the end of the course and for the final. Gauss's law is real important. So divergence of, if rho v is 0, divergence of D is 0, and it also means divergence of E is 0, right? These two are basically the same law, just in terms of E instead of D. What that means is this term right here goes away. Okay, that's based on the assumption. We're building to something called the wave equation. I just want to let you know. So now, if that's 0, I have this equation. Minus del squared of E equals that, right? Now, I'm going to group everything on one side, set it equal to 0. So that means I have del squared of E minus gamma squared E is equal to 0. This is a real important equation. This is called the Helmholtz equation or wave equation. Or really wave equation. But still, I'll just tell you, the del squared of E, this is a vector del squared operator, not a scalar. Anytime you have a del squared, you have partial derivatives, second order partial derivatives in X and Y and Z. I'll write this up here just for one time for everybody. There it is. I'm going to come over here and erase this. This is just, you don't have to write this down, just appreciate this. So when you have a del squared operation on E, E in general has 3 terms. It has some, if we're talking about Cartesian coordinates, this has some EX-AX plus some EY-AY plus some EZ-AZ. And when we do a del squared operator, we take the second derivative of vector E with respect to x squared, all right, plus the second derivative of vector E with respect to y squared, plus the second derivative of vector E with respect to z squared. Now I want you to take a look at this. There are three terms right here for E, right? So that means we have three terms in this adjusted second derivative with respect to x. Follow me on this, class? Three terms here, three terms here. That would mean 9 different terms possible in that equation for the most general form of the solution. You're not going to find a closed form solution for that. All right, not the general form. You have to make assumptions. You can if for spherical coordinates and a few other things, but right now I'm just pointing out to you, if you take that in here and do this, these derivatives, you're going to end up with 9 terms. And you have an x, y, and a z term. It is, by the time you stick that back over here, the solution for it becomes unimaginable. And so what we do is we make assumptions. And the assumptions we make now, I'll write them down here. Now we're talking about, we assume plane wave propagation. And here's what I mean by plane wave propagation. If you, this is going to be the analogy is to really to a physical system. It has to do with really wave propagation on the surface. So if of say a pond, if you drop a pebble straight down the pond, you'll see rings really where a wave will develop and it'll spread out radially. Do y'all follow me on this? Now, as it gets further and further away, the amplitude goes down, but all of a sudden, the radius of curvature gets larger and larger. Do y'all follow me? When you're finally out a long way from there, and you're standing, it looks like you just have a planar wave front propagating in one direction. It doesn't look like it has any curvature. Do y'all follow me on that, class? When we talk about electromagnetic phenomena that are plane wave behavior, we're saying we're so far from the source, there is no curvature. And fundamentally what we have is a wave that's planar, it's really, its radius of curvature is infinite, and it has something where it's propagating in the same direction, and the amplitude itself will only vary, you might say, in the direction of propagation. It will not vary in the direction perpendicular to it. So if you think of an ocean wave, you're a long way from the source, you got an ocean wave, and you were on the peak of that ocean wave, you could freeze time and look down, that peak would go forever in that direction. Do y'all follow me? Now, as you allow time to progress, the peak moves in this direction, right? But still, if I froze time, there's no change along the perpendicular to the direction of propagation. The magnitude's the same. Do y'all follow me? With electromagnetic propagation, you can't imagine it. I mean, you can't look at an E field generally. You can look at optical light and stuff like this, but when we talk about electromagnetic propagation, we're saying we're so far from the source that the electromagnetic field has lost any effects of curvature from the source itself. We're that far away. Now, when we do that, this derivative right here, we're going to also do one other thing. We're going to assume the E field has only one orientation or polarization. And we're going to assume the general form of the solution would be some E field that's going to have a magnitude E naught, and it's going to be propagating in the Z direction. So it's going to have E to the minus gamma Z. I'll explain that in a second. And it will be in the AX orientation. Now I'm keeping consistent with Dr. Wentworth's notation. You'll see how this comes about in 1 second. What I'm really saying is this. If we take a look at the electric field that we're going to be talking about in plane wave propagation, it has, call X up for now, right? It has only an X polarization and it's moving in the Z direction. So it's hard to envision this, but I'm just showing you the actual orientation of the electric field, and it's propagating in this direction. So just imagine, if you will, sort of an electromagnetic wave where the amplitude of the wave would not vary in this direction, all right? If we just look down the head, and it would propagate in that direction. Does that make sense? It's as good as I can do with my hands and stuff, but you'll see this later. So how does this come about? Well, Now this del squared operator only has one essential thing. Now, the del squared operator becomes the second derivative of EX with respect to with respect to Z squared in the AX direction plus, minus gamma squared EX equals 0. I've replaced all those 9 terms that would occur here with only one term because we have a vector that is only oriented in the X direction and propagating the Z. So the only derivative that's going to exist, survive, and not be 0 is going to be this one. You with me on this, class?
Can you say that part about like explaining it, how it varies in one way and
Let me try it this way. So if this is the Z direction and this is the X direction, let's say we have a wave like that.
yeah.
That's at t equals 0. Now that can be the amplitude, say it could be the amplitude of the E field. So the E field would look like this. Remember, I'm freezing time here.
Yeah.
It's propagating out. This wave, if you extended it this way, if you can envision it, the magnitude that would be the same. I'm that far away from the source, no curvature. Now, if you let time go by a little bit. Then all of a sudden, now I'm going to have this type of behavior. Here, it's going to be negative. And I'm not drawing very well, but you can see the peak moving in this direction. That's the direction of propagation. The peak was there, it's moved to here. Do y'all follow me, class? And you can kind of imagine that, right?
Yeah.
Just let time roll on. And that's what I'm talking about.
Okay.
All right. So back to this equation. Now we're here. We're going to develop plane wave propagation. For this one, I'm going to get rid of the AX, by the way. We know it's in the X direction. Now, when I have this right here, I mean, this is a simple second order homogeneous differential equation, right? We could solve it a couple ways. We could do an integration factor, or we could use Laplace transforms, right? Either one. The general solution to this would be what? EX would be E0, call it the magnitude, and it would be E0 plus E to the minus gamma Z plus E0 minus E to the plus gamma Z. Now, I'm putting, this is the general solution.